Hello folks, StylePoint here, and today we're going to be implementing a convolution. More specifically, a 2D convolution. But once we understand how a 2D convolution works, it's pretty easy to think about the behavior of 3D convolution, and furthermore generalize into higher dimensional spaces. And so I think it's going to be very helpful and useful because we're going to be using convolution in the convolutional neural networks as well. They're going to be used for extracting features out of images and more generally out of signals. So this could be an image, again, audio, radar, and so forth, radar data, and so forth. Okay, so let us first explore what we have as far as the code base goes. So I have put together this little program. We have the skeleton function, con2d. Okay, we have to implement that function. That is the convolution. And we have the testing code that I've written beforehand so that we can run the test pretty much. We don't really have a test. It's going to run some matplotlib functions, and it's going to visualize the results that we get out of the convolution, or running the convolution over the image. Okay. Now, some assumptions we're going to make here is that, again, this is a 2D convolution, and another constraint that we're going to have is that we have a single channel image. Okay, the traditional image, of course, we know that's it has 3 channels. It's red, green, and blue, RGB, right? But for the sake of simplicity, and to better understand how the convolution works, we're going to keep it simple again, and have a single channel image. Okay. Now, I have prepared this pretty much. Well, I found a few visualizations on the web. Let's put it that way, and we're going to use these visualizations to better understand how the convolution works. Okay. Usually with convolution, we have 2 objects that we are operating with. The first object is the image, okay? Again, this can be a signal of any kind, really, but for the sake of simplicity, we have an image, okay? In this case, the image is this large thing right here, the bigger matrix, okay? Then we have a smaller thing, a smaller tensor, okay? It's order 2 tensor, again, it's a matrix, 2-dimensional matrix, okay? And what this smaller matrix does is that it slides over the image, okay, which is a bigger matrix again. The smaller matrix is called a kernel, okay, and the kernel is sliding over, or we can also call this operation, or also describe this as convolving over the image, okay, and you can see how this does it, how the kernel does this. It does the sliding window kind of thing, moves one kind of column at a time here, okay? So the kernel is there, it kind of projects onto the image, we have that projection, and then it slides. Well, it does some computations, we're going to explore those computations as well, but it slides, it performs those computations again, slides again, and so forth, okay? Now, here is another visualization that I found on the web. And here again we have this projection of the kernel. Well, this is a kernel pretty much. And it slides over this blue image, okay? The color is blue, but it might not be a blue image. It does not really have any values inside it. But anyway, the point is it performs the sliding window. Now the dotted lines here, those signify, or those show us the padding that we have. What is a padding? Well, initially we have this image right here that is blue, right? It's 5 by 5, and the kernel that is sliding over the image, that is 3 by 3. Now, if we just slide over the image without the padding, we can only do it 3 times. This 1, 2, 3, or we can have 3 projections really. If we want to do it 5 times, well, then we need padding, and you can see 1, 2, 3, 4, 5 projections. And padding is used for that, basically. If the kernel cannot fit, well, we have to pad the image to increase its size. Usually we pad the image or whatever signal we have with zeros, right? It can be some other value as well, but usually it's zeros. And that allows us to basically perform these steps, or do the sliding window more times. And the stride, that is basically like the step size. In this case, it's 1. You see, 1, 2, 3. It moves 1 column at a time. It never jumps over 2 columns of like adjacent cells in a way, okay? So it's like 1, 1, one. That's the stride. Okay. Now, mathematically, here's what we do. Okay. Let's suppose we have this kernel right here, right? And we multiply it by the chunk of the image right here, right? What we do here is, well, let's suppose this is a kernel, 3 by 3. Well, let's suppose these are maybe zeros here. Maybe this is not a good example, but let's suppose this is a kernel right here. It's 3 by 3. What we do is that we take this 0 multiplied by 40, we take this 1 multiplied by 42, we take this 0 multiplied by 46. So we perform element-wise multiplication. We take this 0 multiplied by 46, we take this 0 multiplied by 50, we take this 0 multiplied by 55, we take this 0 multiplied by the 52, take this 0 multiplied by 56, take this 0 multiplied by 58. And then we sum these values up and get 42. And that's the result that we get for the pretty much the convolved image, whatever we get after applying the convolution onto the image, right? That's the value that we get out of it. Here is another example. Let's suppose we have this, maybe this is a better example because this kernel, it seemed as if it's like padded with zeros or whatever. Here's a better one. We have input, it's 0, 1, 2, 3, 4, 5, 6, 7, 8. This is the image, let's suppose, a single channel, two-dimensional image, okay? And we have kernel, which is 2 by 2. We take this kernel, we slide over the image. Initially, we're here, okay? Again, we perform element-wise multiplication of these two little 2 by 2 matrices. We take 0 multiplied by 0, get 0. We take 1 multiplied by 1, get 1. Take 3 multiplied by 2, 6. 4 by 3, 12. So we get 1 plus 6 plus 12. That's 19. There we go. Then we slide over here. We get 0 times 1, 0. 1 times 2, 2. That's 2 plus 8. That's 10. And plus 15, that's 25. We get 25 right there. So you got the idea. This is how it works. We slide over the image using the kernel. We perform element-wise multiplication. Then we perform the reduce operation, which is the sum in this case, and that's the value we put in the output. Okay, now let's go ahead and implement this. This is enough for implementing the convolution. The first thing we're going to do, actually, is that we're going to flip the kernel. And I'm going to explain why. We can do it this way. Flip up, down, and flip left, right of the kernel. The reason we're flipping the kernel is because if we don't flip it, we get a related but a different operation. We get what's known as the cross correlation. And cross correlation, it does not really have all the nice mathematical properties that the convolution has. So I'm not going to go into those properties right now, but basically if we want to implement a proper convolution, we have to first flip the kernel. Otherwise we get a cross correlation, which is related, but again, a different operation. Okay, next we're going to get the image height and the image width. We can extract those out of the image itself using the shape because we imported NumPy and use NP ND array for the image for representing an image. That's the data type. We're going to do the kernel height and kernel width. Again, we extract it out of the kernel. So similar kind of thing. Next, we compute the output height and output width. How can we do that? Well, we can compute it ourselves, but there's a formula. Let me show you right there. The spatial size of the output volume is a function of the input volume size W, the kernel field size K, of the convolution layer neurons, the stride S, and the amount of zero padding P on the board. We don't really need to worry about the neurons and convolutional layers right now, but we do need to worry about the dimensions here. So we have W, that's the input volume size. So that's pretty much the dimension. That is either width or height, or if it's 3 dimensions, something else, the third dimension. Okay, so how can we do that? And, well, we take that dimension, subtract the kernel dimension, add 2 times padding, divide by stride. We actually have to take the floor of that and add 1 to it. Okay, how can we do that? Well, here's one way to do it. We can do np.floor of image height. We can do it that way. We need that extra left parent because we're going to be dividing by the stride and then taking the floor. So minus kernel height plus 2 times padding. We divide that over stride. Add, well, we need that. Let me think. So we need divide by that. We need that. Add 1 to it. and cast int onto it. I think that should be it. Let me think. So int of image height minus kernel height plus 2 times padding over stride. Yeah, we take the floor of this. Cool. Add 1 and convert to an integer. Cool. We convert to the integer because I think by default floor does not really return the integer. And of course the dimensions, the height and width, those have to be integers. And we change this to width pretty much. That's the only change we need to make here for it to work for the height, for the width as well. Next we define the output. By default those are going to be zeros. And it's kind of nice because it automatically accounts for the padding as well, because those are by default zeros. And we can do output height and output width. Then we can do double for loop here. Now we're not going to be aiming for performance here. Again, this is for educational purposes primarily. It can also work in production. If you really want to use it, you can. But we want to understand how this works. So I'm going to use a double for loop here. Again, in the production, it's of course better to use vectorized implementation. So instead of using for loops, we would have some NumPy operations that do vectorization for us. In this case, we just do simple for loops in range output height and width in range width. We can define define output at height and width. The way we do it is we can do image with the height and height plus kernel height, and width width plus kernel width. That's going to be image multiplied by the kernel, because that's the element-wise multiplication. Perform the sum operation and return the output. Okay, so what we've done here is, let me remove the highlighting there. What we've done is we extracted the chunk of the image, the segment of the image, right? And we use it using the kernel height and kernel width because we have to take into account those heights and widths. In this case, we move 2 here because basically that's basically we're projecting onto the input using the kernel. So we have to take into account the kernel height and the width. Okay, simple as that. And we multiply that by the kernel. Again, by default, stride is 1 and padding is 0. Okay, so we don't really need to change anything in the for loop here. Okay. Now, for the testing code, what we do is we use matplotlib's image for loading the image. In this case, we're going to be using the Baby Yoda image. This is the picture of Baby Yoda I got from the internet. Right there. Kind of cute. Baby Yoda. Okay. And what we do is we first convert Baby Yoda picture to the grayscale image. Okay, we convert that image to the grayscale, and this is how you can do it. These are the values for the grayscale transformation. Okay, so we load the original image right here. We convert it to the grayscale right there. And then I define this dictionary. It's not necessary, but I wanted to put all of those plots on the matplotlib canvas in a single for loop, basically, without having to do that over and over again and have some code duplication. So I put this dictionary here that maps to tuples, and the first element of the tuple is the image itself, the original, the grayscale, and the features of the image after applying convolution to it. Okay, so once we apply convolution to an image, we get image features in a way. Well, we usually get an image too, but that image is pretty much like the features of the original image. And we also specify colors for coloring titles, and titles will be the keys of the dictionary. Okay, let's run this. All right, new Baby Yoda. Okay, there we go. We have the original picture right here. We converted this original picture to the grayscale variant, or the grayscale representation. Okay, there we have the grayscale variant right here. And then we extracted features out of this grayscale picture. Okay, we extracted features using the 2D convolution. And you can see the features right here. Right, so in the original image we have colors, it's RGB. Then we only retain a single, we do not really retain, we use that formula for obtaining the grayscale. We don't really retain anything, we map it to the grayscale, okay? And then we extract features out of it. Okay, super cool. So you can see the grayscale picture right here, but then the features of the grayscale image or the picture of Baby Yoda, it does not really have all the information about the picture, right? Some of the information is gone or it's not as visible. Other information is kept, and we can see like the edges of Baby Yoda right here. So these are like the features in a way. Again, this is still a picture, but you can see this is a different kind of picture where we have these edges. We only left what is like maybe important in this case, okay? And this was done using a specific kernel, okay? If we change the kernel, we get a different result, okay? In this case, we used a kernel called the ridge detection kernel I got from the Wikipedia page. So it's -1, -1, -1, -1, 8, -1, -1, -1, -1. And you can see we use that one right here. Now, we can change this kernel. There's a blurring kernel, but more importantly, there's a kernel called identity kernel. I like this one because it shows how the convolution works at a very basic level. Identity kernel. And the way this is going to work, of course, you probably already guessed. We can put all zeros, except for the middle one. And let's run that again. Okay. In the meantime, let's look at this visualization right here. What would happen if I would put 1 right here? Okay, well, it does not really matter in this case. Maybe 1 right there and all zeros, or one right here, all zeros. If I put 1 right here and let the other values here be 0, what would happen is in the element-wise multiplication, we would have 1 times 0, that would be 0, and then all the zeros would zero out the rest, and we would get 0 here. So it maps 0 to 0. Okay, maybe a better example would be this one. This is almost like an identity kernel, except for we have the 1 in a different place. If we had it in the middle, it would zero out 40, 42, 46. Those products would be zeroed out, and we would have 50 times 1, which is 50. So you got the idea. So the result of this we expect to be the same as the grayscale. So the result of applying the convolution, the identity convolution with the identity kernel on the grayscale image should be the exact same grayscale image. Let's see that. There we have it. We can see it. No changes. Initial grayscale picture is right here, and then there is the post-convolution picture that is pretty much the same. Okay, because again we use the identity kernel. It does not change much. And of course, there are other kinds of kernels. I think I had the Gaussian blur there, but there are a bunch of other kernels here as well, and there are a lot more than there is on this page. Okay, so this is how the convolution works. Okay, we use convolution for extracting features out of images, or more generally, we use it for extracting features out of any kind of signal data. Okay, could be an audio, could be radar data, and so forth. Convolutions are going to be very important once we start implementing convolutional neural networks. As the name suggests, convolutional, it uses convolutions. And they are pretty much the state of the art for working with image data or training image classifiers, image generators. So basically for doing AI with images. So that's pretty much modern artificial intelligence with AI, and that uses convolutions all over the place. Okay, so I hope you found this helpful and informative, and that's going to be it for this video. I'm going to see you next time.